Today on Macaulay Math, we're going to optimize everything. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 19 on optimization. Our goals for today. We're going to solve applied maximum and minimum problems. One of the main uses of calculus is to optimize functions. In general, the process is simple. A maximum occurs when a function changes from increasing to decreasing, and a minimum occurs when a function changes from decreasing to increasing. The points will naturally have a horizontal tangent line. The derivative is particularly good at finding horizontal tangent lines. Thus, when you're asked to optimize a function, find the first derivative, set it equal to 0, and solve for the independent variable. This lesson, similar to the last lesson, isn't necessarily about learning new mathematics. It's about using the mathematics that we currently have in real-world situations. And a lot of times when you come across problems where they ask you to find the maximum or the minimum or an optimum solution, they are asking you to use calculus in a way where you are finding the first derivative and setting that first derivative equal to 0. And we know that we need to do that because that is where maximums and minimums exist. So we're going to have some guidelines for solving maximum and minimum problems, and then we're going to do an easy, medium, and a hard problem. And again, I would suggest if you are using the slides to follow along that you might get yourself a couple extra sheets of paper, because the solutions to the last two sets of problems will not fit into a single page. So first, what we want to do is we want to start talking about just some general ideas and some general guidelines, because you can't follow these rules step for step, but they give you an idea of what you want to do as you move forward. And the first thing you want to do is you want to identify all of the given quantities and all the quantities that need to be determined. If possible, then make a sketch. You want to write a primary equation for the quantity that is to be maximized or minimized. And then you want to reduce the primary equation to one having a single independent variable. This may involve the use of a secondary equation relating the independent variables of the primary equation. We're going to do that a lot in this lesson. So number 4, we're going to determine the feasible domain of the primary equation. And what that means is we're just going to determine the values for which the stated domain makes sense. Because there's going to be some equations where the algebra says that there's a lot more solutions in the domain, but they won't make sense in the context of the problem. And then finally, we're going to determine the desired maximum or minimum value through calculus techniques. So what does that look like? Let's start with an easy one. First, find two positive numbers that satisfy the given requirements. The sum of the first number squared and the second number is 54, and the product is a maximum. So right off the bat, they're telling us that we need to maximize the product. All right, now normally if I have two numbers, let's call them the product is equal to x times y. There is no maximum unless there's some additional information, because if you pick two numbers, let's say 30 and 40, well, I could pick 31 and 41 and that would be bigger. So unless there's something to limit what those values are, there isn't necessarily a maximum. But we're going to start by calling this our primary equation. And then we're going to look for some additional information. And that additional information is the sum of the first number squared and the second number is 54. So x squared plus the second number we'll call y is equal to 54. Now what that does is that says that I couldn't possibly pick 30 and 40 because 30 squared plus 40 is going to be bigger than 54. So our numbers have to be smaller than that. So we're going to use this secondary equation to limit what's happening in the product. And so there's a number of ways to do that, but solving for y is fairly easy. We can say y is equal to 54 minus x squared. And now we can substitute into the primary equation. And what that'll look like is I'll go p equals x times, and we'll substitute in for y, this 54 minus x squared. And here I'm going to distribute, and I'll have p equals 54x minus x to the third. All right, now I know something about this equation, and off to the side, I know that it's going to go through x. It's going to look something like this, I think. And it's going to go through 0, 0. And then this will be square root of 54, or negative square root of 54. And this one will be positive square root of 54. And we're looking for this maximum right here. So nothing in this part of the domain and nothing in this part of the domain is going to make sense. So from 0 to square root of 54 is where we're looking for. And we're going to try and maximize that. And the way that we're going to do that is we're going to take the first derivative of p. And so I'll get p prime is equal to 54 minus 3x squared. And so we're going to set this thing equal to 0. And so we go 54 minus 3x squared equal to 0. I bring the 54 over, negative 3x squared equals negative 54. 3 goes into 54. Well, 3 goes into 5 once, and that's 2 left over. And then 3 goes into 24 8 times. So I've got x squared equals to 18, and the negatives cancel. And so if I take the square root of both sides, I get x equals plus or minus the square root of 18. Now, we already know that there's got to be 2 values for x that make it equal to 0. There's one over here, and then there's one over here. And we want the positive one because the negative one doesn't make sense. So what we're going to do is we're going to say that x is equal to positive square root of 18. Now, square root of 18, you can factor out a 9, and you can say that is the square root of 9 times 2. So my x is going to equal to 3 square root of 2. All right? And so that's my x value. And since my x value, I know I can plug it back into this y equation, and I can take that x value and plug back into the equation for y. To get my final answer. So y is going to be equal to 54 minus 3 square root of 2 squared. Now we already know what 3 square root of 2 squared is. It's 18. And so y equals 54 minus 18, which is 36. So our final answer, 3 square root of 2 and 36 maximize the product. All right, next example. Determine the dimensions of a rectangular solid with a square base with maximum volume if its surface area is 337.5 square centimeters. All right, so we are trying to maximize the volume of a rectangular solid. So volume equals length times width times height. Now, again, we have a problem here. We've got 1, 2, 3 variables that our function is defined upon. That's not good. But we do know some other information. First off, we know that this thing has a square base. So if I draw myself a little diagram over here, I know that my length and my width are the same, and I have a height. So already I have changed this down to a x squared h equation. Now we're down to 2. All right, that's not so bad. But again, just like in the last problem, if you have no other constraints, then we can just keep making x and h larger and get bigger and bigger volumes. But we do finally have one last thing that limits our values for x and h, is the fact that the surface area has to be 337.5 square centimeters. All right, so how do I calculate the surface area? Well, the surface area is just the sum of the areas of the sides of this particular rectangular solid. So how do I calculate that? Well, the top and the bottom are both x squared, x times x. So my surface area, which I'll just call A, I should, just to keep the variable simple, it'll be 2 times x squared. Why? Because I have a base that is x by x, and I have a top that is going to be x by x. And then it's going to have 4 sides that have a width of x and a height of h. So it'll be plus 4xh. And I know that this A has to be 337.5 square centimeters. 2x squared plus 4xh. All right, so I could solve for x, but then I'd be taking a square root, and I've got a square here, and I've got an x here. H is kind of all by itself, and so I'm going to just try and solve for h. And so to do that, I'm going to subtract, well, first let's do this. And to do that, I'm going to subtract 2x squared from both sides. That'll give me 4xh is equal to 337.5 minus 2x squared. And then we'll divide by 4x. And that'll give me h equal to 337.5 minus 2x squared all over 4x. Now I know that that's kind of ugly, but I'm going to plug this in. Primary. And so I'll have b equals x squared times 337.5 minus 2x squared all over 4x. Now I can get one of the x's to cancel from the numerator and the denominator, so I'm going to simplify a little bit here. I will get v equal to, I'll get one of the x's to cancel, and so when I distribute, I'll have 337.5 x minus 2x to the third all over 4. And now I have a primary equation that is only in terms of x. And this thing I'm going to derive. Now to simplify that a little bit further, I want to get this 4 as a constant. So I'm going to make it v equals 337.5 all over 4x minus 1/2 x to the third, because 2 over 4 is a half. And now v prime is just going to be 337.5 all over 4 minus 3/2 x squared. Now this thing I want to set equal to 0. And we'll get 337.5 over 4 minus 3 over 2 x squared equal to 0. And here I'm going to subtract 337.5 over 4. So I'll get negative 3 over 2 x squared equal to negative 337.5 over 4. And then I'll divide by negative 3 over 2. That'll give me x squared equals negative 337.5 over 4. And when you divide a fraction, you multiply by the reciprocal, so it'll be times negative 2 over 3. And let's see here, that'll give me x squared equal to, it'll be positive, I'll get a 2 to cancel out, it'll be positive. I'm going to simplify, and then we'll take the square root of both sides. So I'll have x equals plus or minus the square root. 2 times 3 is going to be 6 in the bottom, and it'll be 337.5 on the top. The negative doesn't make sense in the context of this problem, so our x value, when you plug that into the calculator, and you can do this on your own, turns out it's just 7.5, and it comes out even. This crazy square root actually comes out to be a fairly solid decimal. And so right off the bat, we know what the base dimensions are. It's 7.5 and it's 7.5. And so I need to plug this into the h equation. And so I come right back up here. H is equal to 337.5 minus 2 times 7.5 squared all over 4 times 7.5. And you can plug this into your calculator, but it also comes out to be 7.5. So my final dimensions, are 7.5 centimeters by 7.5 centimeters by 7.5 centimeters. All right, that says that a cube will maximize volume with a given surface area.